Good afternoon. My name is Robert Warren. The title of this talk is Paradata, Realism, and Documentation with Historical Games. This talk is the results of a number of projects and publications with David Evans, Minzy Cheng, Mark Farrell, David Miles, and Eric Campion. I'd also like to single out Sean Graham and Ian Milligan as other guilty parties. I apologize that I can't be there at the conference today. My colleague David Evans, who I've known for a very long time, passed away this week, and I was unable to take care of conference work, travel, and David at the same time. I will be there tomorrow in the afternoon for further conversation. So the background to this work has been a long time in coming and began with very complex modeling and operations research. And the problem there was really, how do we reference very specific pieces of data instead of scholarly work? And at the same time, we were working with very complex modeling of operations, very complex databases that were documented in very nauseating models, as well as a project on the First World War that was generating lots and lots of data, but with a richness and a complexity and a strength that was difficult to represent within standard tabular reports, and it was very difficult to communicate them to subject matter experts such as historians. So from that was this series of papers that were dedicated to how do we explore data that is very complicated and to subject matter experts who don't necessarily have the modeling or the data reporting expertise to really work with these very complex machine-readable data sets. And this becomes very important when we look at the volume of digital and machine-readable data that is coming out of the archives, which is increasing in terms of volume, but also in terms of the complexity. And it's no longer sufficient to simply reference a particular call number within an archive, because we're now looking at subsets or derivative products of those archives. Concurrently, the problem of reproducing experiments and studies and specific scholarly works is raising its head because the devil is in the details. And we're taught as scholars to write papers that are pleasant to read and informative to the reader. But if we really put all of the details necessary to reproduce experiments within a paper, we tend to get a rejection because the people turn off. And really, a lot of the technical aspects of experiment generation in this day and age are of such a specialist nature that they tend to turn off even the most hardcore scholars. So how could we look at data, document how the data was built, without necessarily burdening the narrative that we communicate from one scholar to another? And to answer that, we looked at video games for data exploration. And the reason for that is that it was very intuitive. What you see in front of you is what you get. And video games as virtual environments tend to be very forgiving. From time to time, some of the data is inexact, and the data is marked as inexact. But visually within that virtual environment, it's not always possible for the actual user to determine that there is an inaccuracy. And it may not actually matter if there is an inaccuracy to the user. Lastly, there is the question of procedural generation. And procedural generation is very interesting when we have very large complex databases that have bits and bytes of data that nobody actually knew was in the database, but the procedural generator that's online can actually go through all of this data, pick up items that we weren't quite aware of, and still generate a very good reporting system that actually makes sense to a domain expert who's not an expert on the data itself. And this was an early prototype. And this is a virtual world that is the Vimy Ridge era 1914. And one can walk around in the trenches as they were in 1914. And the accuracy of this terrain is about 5 yards. Now, if you look at the top in the middle, you'll see there is a longitude and a latitude, a date, as well as a time. And the simulation was made to be very exact. So everything that you see within the simulation is derived from a specific piece of data. And the sun is in the right place in the sky for that time and the date. And the trees that you see are actually marked in a map as being there. So it's a fairly interesting way of looking at data in that everything that you see has some traceability and some provenance back to a primary source document that tells you what was there at that time. The real problem from Earth's perspective is that data wasn't enough. And we may have the actual maps from that era that documents where everything was. The problem is the transposition of that data to a modern coordinate system requires a lot of decisions about how that translation was going to be done. And depending on what your beliefs are on those documents, you can be 300 yards or 1,000 yards off within that specific map. So it was not enough to talk about the data. We had to talk about the processes behind data and as well as the beliefs behind the data. Similarly, sometimes there were landmarks that were marked on the maps, but the size or the state of those landmarks was not necessarily documented. So now if we're going to represent that visually, that needs to be documented also. And it may be based on a mathematical process, but that process needs to be documented also. And lastly, every game designer in the universe will actually put an aesthetic aspect into generating that virtual world in order to make it pleasing to the end user. But that needs to be documented too. And the problem is, we do this in order to make it pleasing and entertaining to our audience, but we know from other studies that it takes 2 to 3 times more time to actually document something than it does than to create it. Or if in very layman's terms, you have to measure twice in order to cut once. So the people that create these environments in these games are in a rock and a hard place in that they have to document everything, knowing full well that an educated and interested user will only ask about certain aspects of their work that they may not be able to predict. So they don't necessarily get the benefit of doing that work. And finally, well, it may or may not be what somebody is interested in, so it may not matter at all. So in terms of creating paradata, provenance, and document, it's a very expensive process and a really annoying one. Now to contrast some of these things, I'd like to put 2 simulations one next to each other. On the left is the simulation that we did from UNIN of 2 years ago, and on the right-hand side is an undergraduate history project created by Ryan Pickering, who is one of Sean Graham's former students. Now, on the left was an effort to make a very documented, very realistic simulation of Vimy Ridge. On the right-hand side is the very pixelated world of Minecraft. And on the left and the right, both the same primary documents were used to create that specific world, but to a very different way. So on the left, we translated all of the maps into longitude and latitude in WGS84, and then it was moved into a UTM coordinate system so that the Euclidean space of the game actually fit within real-world coordinates. On the right-hand side, Ryan simply took the image of the map and converted it into an actual Euclidean space that just fits directly into the game. So these are bound projections. Within this case of both simulation, it actually doesn't make any difference to the user, but in the left-hand side, we still have that the relationship to the real world, and the coordinates at the top actually update as you move around within that world. So there were 2 different objectives here, and that one was made to be very documented mechanically, while the other one was created with paradata in mind. And this is one of Ryan's paradata document, which is created using HTML. Now, he had a lot of work put into this, and this was work on top of the actual design that he did in Minecraft. And this is a bit annoying because you're doing the same work twice. You actually have to do the work, and as you're doing it, you have to write this document about how the work was created and what the primary source was. So it's this annoyance in that As scholars, we may have a question about how certain parts of that simulations were built, but we actually have to perform some kind of information retrieval on a narrative which we may not have the time to go through, and most of the narrative is actually not of interest to us. So there's a mismatch about how we create paradata versus in how we actually consume it. And while this is perfectly reasonable to do on a small scale, what happens when we go on a very large scale? As an example of this, let me go back to the trees. Let's say we have vegetation. The map says, okay, we have a tree here. And the map doesn't tell you anything about the tree except that there's a tree here. And now our simulation has to make a decision about that. And the tree needs a certain height and needs to know certain circumstances so that the renderer can actually put it on the screen for the user. And what we can actually do is go through another historical database and say, are there any trees nearby? Can we actually have a probabilistic estimate of what the tree should be? And that probabilistic estimate is what is passed on to the renderer. Now, again, the map, this is a battlefield in the First World War. There is no information about what the state of the tree is, so we end up with beautiful looking trees that have been shot at for 6 months, and that simply is not realistic, but we have no information with which to make that decision. And so we end up with this type of rendering. Now again, my map doesn't tell me what type of species of tree actually grew there, so we need to make a decision. And what we did in this particular case is the algorithm will actually, knowing where in the real world this specific simulation and tree are, will just look it up in another database and assign randomly a specific species of tree to that tree based on what is reasonable. So in this case, it picked a European ash that's growing in the middle of a battlefield. And what we've done with the paradata is that by clicking on each tree, it can tell you exactly what specific tree is growing there and give you more information about where that data came from. Now again, this may not be representative of the specific tree that was there at that specific time, but it is a reasonably educated guess as to what could have been there. Now, it's reasonable, but it needs to be documented. And here's a very rough representation of what that process is. Well, the map says that there's a tree here, so we have a process that generates the tree. And that process needs to know what size of tree there is, and in order to determine that, it picks a statistical size from other trees that are nearby. And it also needs to know what species it is. And since there's no information, it will retrieve simply the location of that tree within the real world, say what type of area and what type of fauna is there, look it up in another database, and randomly pick a tree that is possible as growing there. So all of this is statistical in nature, except for the primary document of the map. But as we generate the decisions that allow this tree to be rendered, we also document it at the same time, which allows us to later on tell the user, well, was the fauna representative of what was on the battlefield? Well, it is likely, but it is not certain. So why am I talking about this? I believe it's an eventual necessity. As it is, we have a lot of procedural generation that functions behind the scenes that are making decisions about these games and that are making decisions based on data. But there is too much data and there are too many algorithms running in the background for us to simply assume and trust the system. But conversely, what is perverse about this is that the amount of data that it's generating and its complexity is such that we require other programs to actually read that data to tell us what is in there. And a number of people are very uncomfortable with using user agents to process data. But to me, it's the best of both worlds in that it unloads all of the processes that are tedious and annoying for us to do, such as generating paradata, onto the computer, which is fairly good at it, while allowing us to only retrieve the paradata which we think is relevant to the specific research question that we have in mind. And in the case of online procedural generation, it allows us to keep track of all of the decisions which were made, which we may or may not care about in the future, but it's been recorded in case we really do want to look at it later on. So 2 items that I'd like you to remember. The first one is, as the amount of information grows, information that has not been designed to be found is likely never to be found. And, we're scholars, we like to write narratives, but given the amount of information growth, if your paper is not properly indexed, nobody will look at it, just because nobody has the time to actually find it. The second one, and I think this is self-evident, is that if you cannot explain how your algorithm works, you can't defend it as being correct. And the corollary to this is, if you can't explain what data your algorithm is using, why it's being used, and how it's being used, it's very difficult for you to actually defend the results of your observation or your conclusions as a scholar. I was talking about the need to use user agents. And this is a very early prototype that we were playing with in terms of online procedural generation, where after each simulation, the computer will actually generate credits using all of the paradata that it generated while creating the simulation. And credits are something that work well within the TV and movie world, and to a certain extent in the gaming world, but it allows you to give credit to the data providers that you use to create that simulation. And it reacts very well to the fact that you may change which data provider and which pieces of information you use to create that specific simulation. I'd like to leave you with a very small example on the importance of paradata. This is a representation of an infantry skirmish within a video game. And within a video game, it's very easy to code things such as minimum distance in between non-player characters. Now, infantrymen, since the very dawn of ranged weapons, have learned that it's very important for them to keep distance from each other, because if they're too close to each other, they create a very large target for a marksman to shoot at, and they increase the probability that they'll get hurt. Now, trigonometry occurs for everyone, and in this case, it requires a lot of coordination for infantry to actually keep their distance, and it requires coordinations for marksmen to actually concentrate their firepowers at the same time. So there's a very strong social connotation to this. And one of the things that was learned during the First World War is the importance of not only keeping your distance from other infantrymen, but breaking up the line as it advances, because it makes that trigonometric problem for all the marksmen to concentrate their firepower much more complicated in trying to concentrate fire on a single individual. Now, how can we encode these advances, and how can we encode, say, the reverse behavior, which is unwanted behavior that happens when you have low morale or low unit cohesion? So, for example, untrained infantrymen will try to congregate together in people that they feel safe with, and that might be their unit, or that might be people that they know personally. And we can get that data from other documents. And in case of personal relationships, we can get that from their next of kin documents and create a social network from that. Or in terms of unit cohesion, we can look into the files and figure out which soldiers were part of which platoon and assign those identities to non-player characters. So we can simulate these behaviors of line advance in a very specific and realistic way, or these behaviors of bunching when morale is low, based on either social or structural decisions. But there's 2 parts here, which is there's the data that tells you where these people are from and who their kin are, and there's this other data that tells you what the command structure that they're dealing with is. But there's also your decision of saying, this is the specific behavior that I believe is appropriate in this case. So paradata is much more than just saying, this is the specific data that I'm referencing. I'm also saying this is how I'm going to use that data, and this is the specific style of usage of it that I want from it. So really, data-driven procedural creation is dependent on creating that data not only to document what data you use and how you used it, but the specific reason that you used it that way. So you may believe that the training and the command structure is what drives this particular group of people to function the way they did in that specific case. and you can document that through Paradata. Now, somebody else might not believe that and disagree with you, but that does not take away from the correctness of your simulation. And I think that's very important in terms of scholarly work, in that we allow ourselves to disagree with the conclusion of somebody else while not disagreeing with their simulation. So I hope you enjoyed this presentation. What I really worry about is that with the amount of data that's being created, we're making everybody's job harder, and we're not giving to Caesar what is due to Caesar. Computers are exceptionally good at keeping track of data. They are exceptionally good at making decisions based on algorithms that are tedious and annoying for human beings to do. Human beings are very good at making decisions at a high level and making narratives that argument those specific decisions. But what I would really like us to see is to go towards a direction where the Paradata is very much a structured piece of data that we reference from a narrative in saying this is what we were trying to achieve in creating this simulation without necessarily spending our time creating data structures. Thank you for your time, and I look forward to seeing you tomorrow.